you want to talk from this, or you want to talk up here?
I knew I took ballroom dancing for a reason. Welcome, everybody. It's great to be here. My name is Glenn Ricart. I'm the founder and chief technology officer of US Ignite, as you've just heard. I'm also adjunct professor at the University of Utah. And so I've got the University of Utah symbol up there in the upper right-hand corner. Give them due credit. The work I'm reporting on was funded by the National Science Foundation, and they would like credit too. So they've got a logo up here indicating that. US Ignite, where did I take this picture? What's it a picture of? It's Chicago, yes, that's right. Where was I standing when I took this picture? Navy Pier, that's correct. On the south side of Navy Pier, and that's looking back at the city just after sunset, so you get that nice little red streak there. So that's what that is. So I started with a little bit on who is US Ignite. Could you turn down my volume a little bit? I like to talk louder. So amplify me less so that I can talk louder. Thank you, I appreciate that. So US Ignite, who is US Ignite? Well, US Ignite is a nonprofit that works at the intersection of academia and government and industry. And we work with all three of those partners. And here are some of the projects we're working on. At the top left is visualizing pipes underneath the concrete using augmented reality in a smart city. And I'm going to show you more about that one. The top middle one is real-time communications to a fire zone out west. These are drones that are sent up to go and relay real-time information about the fire and real-time communications to the firefighters. Public safety application. This one's done out of the North Texas Emergency Response Center. On the top right there, these cute little guys are Gigabots out of Kansas City. And they are cost-reduced robots. And the reason they're cost-reduced is that their intelligence is interactively streamed to them. So there are a bunch of sensors and motors and a communication box. And all the intelligence is streamed to it, so it has that kind of, you can make it smarter without even touching it, just the way that your Alexa understands more commands without touching it. It's just streamed to it. So this idea of streaming intelligence to the device means it can be cost reduced, makes it a lot less expensive, and more flexible. These guys run around in senior citizen living facilities and monitor for carbon monoxide, fallen occupants, other kinds of dangers that might exist in the apartment. To my right here is an arrangement of a 4K microscope. It's actually a 5K camera. It's a Red One camera that they use for motion pictures, mounted on top of a science quality microscope. It's looking at, in this case, those round things are called diatoms. They're found in Pacific Ocean water. And students in Chattanooga, Tennessee are studying mechanisms that live in Pacific Ocean water. And I'll show you a video on that too. This is the symbol for power right here. I think we kind of liberally borrowed from the Wi-Fi symbol and put it over the United States. And let me tell you a little bit more about power. Power is an agreement between 30 of the world's leading communications companies, the National Science Foundation, and US Ignite to go and form 4 advanced test beds, which we call platforms. It's very interesting. We were going to call them test beds, but then people said that, well, test bed implies a certain configuration that I have to test in. And it's really something that people can do whatever testing they want. So we're going to call it a platform, which means that you can reconfigure this, put in your own antennas, put in your own waveforms, put in your own UE, whatever you want to make it for you. So the 30 companies have put up $50 million. The National Science Foundation is putting up $50 million. That gives us $100 million. We're dividing that among 4 of these platforms. The first 2 are announced and are on the screen behind me here. The top one is Powder and Renew. It was actually 2 proposals at one time that got married. Powder is from Salt Lake City, and there's great powder skiing. I live in Salt Lake City. But I recused myself from the evaluation, so I didn't have anything to do with putting my thumb on the scale. It just happened to come out that way. We have about 2 feet of snow already at the ski resorts. They're not running the chairlifts yet, but very soon. Together with Rice University, Ed Knightley, and they do a lot of good work on MIMO and massive MIMO. And in fact, they're looking at 120 by 120 array MIMO. to see if we can have truly massive MIMO, which if it's true will really multiply the bandwidth that we've got available. And then Cosmos is a joint production of Dipankar Reshaduri at Rutgers, Ted Rappaport, NYU, Columbia University. And that one, the first one up there is 6.5 acres of downtown Salt Lake City, and then a residential corridor, which is a little bit less populated. And then Cosmos is running on the Upper West Side of Manhattan near the Columbia University campus, including Silicon Harlem. So they're looking at millimeter wave, microwave. They're looking at very low, very, very low latency, as in microseconds, and less than that if they can get away with it, and very, very high bandwidth, because once you get up to 130 gigahertz, you can really modulate that very quickly and push in very big data rates. So that's what's going on there. And I'm not going to mention it again, so I thought I would at least, given that this is a communications conference, mention this communications stuff that's going on. The other logo here is of our smart gigabit communities. And that's my main talk today, is real-time communication applications and services that we're working in these 36 communities. 15 of them were funded by the National Science Foundation. The other 11 have come in on their own or with sponsors. And we're continuing to grow this. If you have a good community that you know should join this group, we'd love to have them, because we're trying to create a movement for these advanced applications and services. And that movement depends on showing success and growth in applications and services. So with that, let me move to, I guess I have a big version of that. Let me move to what the actual applications and services are. And then I have a few comments on what they are. We're in Kansas City with 1,700 attendees from 400 different cities and 250 different exhibitors. US Ignite forges partnerships. We bring together academics, industry partners, community and civic leaders, people who care deeply about their community, to help make the transformational change that smart and connected communities can provide.
Largely what we're doing is helping cities define their vision as a smart city of the future.
People are willing to bring these technologies in, but they have to be accessible. So the challenge is relevancy for people's lives. And once we can do that, all the other issues take care of themselves.
So US Ignite is a terrific team at talking at the levels of mayor's offices, CIOs, right in directly into city government. They're a perfect pipeline for that.
In an area like smart and connected communities, it really all is about partnerships.
US Ignite is extremely community focused. The Smart Gigabit Communities program is a perfect example of that. And that's very consistent with NSF's vision of bringing research and innovation to communities.
What we're hearing are personal stories about people whose lives have been changed through our work.
US Ignite and Smart Cities effort has been really great. They've been very supportive of us. I feel like, both in the education space and then just more broadly, there are a lot of really cool applications. So it's really inspirational for us to come here and to see all the cool things that are happening.
This is a conference of doers, people who make things happen in their communities.
US Ignite has always been a place, a convening place. It's always been a clearinghouse for ideas and equipment and money and resources and people, where we can go ahead and test new ideas and try things out and build demonstrations.
The movement we're creating among innovative, smart communities is personal because it is directly affecting people's lives.
US Ignite creates new opportunities.
Relationships.
Innovators. We've built a movement now
to bring life's most important connections to our communities. And that is very exciting.
Okay, so that's what we're doing. We bring people together. I do some research myself. I have a few academic papers myself, but mainly we're bringing folks together to make things happen. So what are these applications? I put them in some categories, public interest categories. So the first one is transportation. In transportation, these are just a few of the applications we're working with. Let me start at the top right. This is an application that's running in Madison, Wisconsin, one of our smart gigabit communities, where the bus stops are instrumented with people counters that are looking at how many Bluetooth and Wi-Fi signals they see standing near the bus shelter. So if you're within about 25 feet of a bus shelter, it's going to go and count you and then generate a heat map for the people dispatching the buses, saying we need more buses, fewer buses on this route in order to go and pick up all the people. And this is especially important when there's events, students are moving for a football game, things like that. And they've got this live, real-time for not only where are the buses, but where are the people who are riding the buses and where they're getting on and off. This is something called smart pavement. I don't remember if I left in the smart pavement video or not. And on the left-hand side there is a project done by Mina Sartipi where you can see through the car ahead of you so that you can see if they might be braking for a child in the street before you see their taillights. So you see how you, instead of looking at the back of the car, who cares what the back of the car looks like, you're actually looking through the back of the car. I think I do have a video on that one. And let me see if I can play that.
My name is Mina Sartipi. I'm with University of Tennessee at Chattanooga, and I also lead the research program we have on urban science and technologies. One of the projects we're working on is on transportation. We're working on fleet management of connected autonomous vehicles in extreme urban environments. Autonomous vehicles, they're almost everywhere now. Because of the advancement in the technologies, they are accelerating, and also we're seeing them more and more. One of the things is they are focusing on each individual car. They are equipped with a lot of sensors, and they are using those sensors to know where the car is and how can to get to its destination. We're counting on a lot of information that it might not actually exist. Like, what if GPS failed? If maybe a sensor failed?
We are talking about transportation. Even 1 second delay is too much. We want to have a real-time data that can be transmitted in real time and a decision can be made.
So that's where we came up with the idea of maybe we also need to allow them to be connected together and, talking with each other, sharing their information, sharing the information from the infrastructure, and using all of that, making a more intelligent decision and be more reliable and efficient. US Ignite, to me, ignites the deployment and development of applications that require gigabit internet connection. Smart cities would be helping improving the quality of life of citizens. We would be doing the same thing that we're doing now, but more efficiently and effectively.
Majority of these technologies are focusing on how can we equip each individual car to have enough knowledge about where is it, how can get to the destination safely and reliably.
I get to work with people that are working on the ground on these projects. They are working with the city. They are the ones that are telling us what are the problems. And what we are trying to do is really trying to help them to address this problem. And this is a collaboration that I've never done before. A very close relationship that we have with the society, with the community, that comes with a real problem that they are having. And we are seeing that how can we address that? How can we help them, fixing some of those issues?
So we have about 104 applications now being developed in various areas, but I picked out the ones I thought involved real-time communications. So real-time communications from the bus stop shelter, real-time communications to go and bring the camera image to the car behind it. How do you do that reliably in real time? Because if you put in a delay of half a second in that see-through video, you've just defeated the value of the see-through video. You have to have extremely low latency, and we hope apparently instantaneous to make that all work. And then this is a new kind of pavement that talks to the cars, and the cars talk to it in real time, and it can provide information to the driver like you're driving off the road.
Today we have smartphones, smart appliances, smart cars, and even smart cities. But our roads are still just roads. But what if our roads of tomorrow could become a digital network, connecting drivers with real-time information, supporting driverless vehicle technology, and providing true connectivity between smart cars and smart cities? Introducing the Smart Pavement System from Integrated Roadways. Factory-built pavement sections, 4 times longer lasting than traditional asphalt pavement. Embedded with digital technology and wireless connectivity to transform ordinary roads into smart roads. Each interlocking smart pavement slab has upgradable digital technology that provides a seamless internet connection to vehicles on the road. drivers will enjoy real-time information about traffic, road conditions, or accidents. In fact, smart pavement technology can automatically call for help if there's an accident or a vehicle leaves the roadway. Much like the trackpad on a laptop, sensors in the pavement can feel the positions, weights, and velocity of every vehicle on the road, providing superior navigation for Level 4 autonomous vehicles, in addition to capturing valuable traffic and usage data. And like a smartphone, the Smart Pavement platform has unlimited potential for third-party applications and services, which means our roads will actually generate income from value-added services. The smart roads of the future will be self-funding and not require tolls or new taxes, enabling us to upgrade public infrastructure without requiring more public money. Smart pavement technology isn't some far-off concept of tomorrow. It's here, today. And Integrated Roadways is already partnering with various state departments of transportation and municipalities to bring our highway system into the 21st century and beyond, turning our roads into smart roads and connecting the smart cities of the future.
So we're working with Colorado Springs, Colorado on this particular roadway. Well, let's look at energy. On the bottom left is a map of Chattanooga, Tennessee, the Electric Power Board. They have a number of storms that occur there because of the surrounding mountains. They end up with some severe weather that gets kind of trapped in the geography there. And as a result, they had a lot of outages. And they decided that they were going to go and put in a smart electric grid that could do automatic restoration. It doesn't require somebody to throw a switch in the central office. It doesn't require somebody to go out and do something on a pole. It's all controlled by fiber optics. And while they were doing the fiber optics for this electric power system, they also went and put in the nation's most complete internet service, because as long as they were running fiber to all of their substations and poles and customers and using it for meter reading, why not also allow it to provide internet service for their customers? So they're running 10 gigabit service for their customers in Chattanooga, and $70 a month to go match the universal Google price. It's amazing how the Google price sets the whole marketplace for what gigabit internet looks like. And this is just a frame shot of where one of their outages, the red are the customers who are out at the moment, the blue are back in service. And in this particular example, it took them 3.5 seconds to get every customer back in service by rerouting their power, all done by computers in real time with real-time communications. So real-time communications turns out to be very important. The top right there is one of the new GE Current electric street lamps that's being installed in San Diego, another one of our smart gigabit communities. And in San Diego, you may see underneath the bevel there is a place for cameras and environmental sensors. And they're using 4 and some experimental 5G wireless to go and have these street lights connect together to the city to make that happen. So real-time communications from the street lights. On the bottom right here is about energy management and real-time energy management. I decided it wasn't real-time enough because they were talking like seconds were real-time. And I don't think seconds are really real-time. I think you have to count at least milliseconds, right, to be real-time. Do you agree with me? Some people nodding. So I'm not going to show you this one because I don't think it was fast enough. Let's go take a look at healthcare. Where's Ken? Ken from Comcast? Here you are. Okay, so there's the picture of the rehabilitation there in the upper left-hand corner. I was talking to you about at lunch. And this is a remote camera that's actually a Microsoft Kinect doing a point cloud so that we know where all the limbs are and what angles they're at. And they're evaluating rehabilitation. In this case, I forget whether it's a hip or a knee. The person in blue there is Dr. Marjorie Skubik from the University of Missouri, Kansas City. And she's working with somebody at home to see if the range of motion is improving and can get direct readouts on her screen of how much that's doing. She's modeling for the patient who's on the left there. She's saying, please do this. Can you do this? How high can you raise your knee, and so forth. So real-time communications is kind of like video conferencing plus being able to measure the limb movement exactly with the Microsoft Kinect box in addition. Bottom left is a real-time communication project, maybe you would consider it. Children wear sensors to show what their personal pollution environment is, and it's very effective in getting the parents to stop smoking around their children. Once they see the sensor turn from green to yellow to red in their very presence, and they realize that's what their kid is breathing, it's been very effective at reducing air pollution for kids. So I guess it's a kind of real time, but not so much communication. Communication by light, maybe. This big picture here is in Utah. The Utah Education and Telehealth Network is doing real time to remote locations, in this case Moab, Utah, where somebody has had deep brain stimulation tuning. So if you have an essential tremor, maybe Parkinson's or something, we've discovered that there are parts of the brain which are activating this. And if we can get that part of the brain confused and thinking about something else, the tremor will stop. So in deep brain stimulation tuning, you stick these electrodes into the brain. So they look like long knitting needles. They've got little active points on all sides. So dozens and dozens of points on each of these needles. And the question is, what waveform, at what frequency, at what intensity should we play into each electrode? You can see there's a gazillion possibilities here of what to go do. It's been simplified in this map on the lower right here. You can see that they're energizing, that red there is energizing the end electrodes in this needle. They're trying to get it into the hypothalamus, where some of this tremor occurs. And as they put the waveform further down I'm going to call it a knitting needle because I don't know what the right medical term is, and get it closer to the actual hypothalamus, they're able to quell the tremor. And so they do that and have to do it repeatedly because the brain keeps having plasticity and adapting to the waveforms that come in. But almost always you can find a waveform that quells the tremor permanently. And so that's what's being done at the bottom right there. And that tuning can now be done from Moab, Utah, because we can read these things out at gigabit speeds and in real-time communications, push back the right waveforms to go and say, how about this, how about this? Go home and come back in a week and tell me if that's still better or not, and we'll try again. So that's what's going on there. Real-time communications. Does it have a name for the thing? Deep brain stimulator lead. Okay, it's the lead. I'll remember that next time. Okay, so that's healthcare. Here's something about education, and these are both worth seeing. So I've got two videos here. I think we're going to do the microscope and the diatoms first, if I recall correctly.
Ever think about the micro world that surrounds us? That fascinating world that is critical to life on Earth and yet is otherwise invisible to us? Well, kids in Chattanooga, Tennessee are about to learn about this world in a whole new way. Thanks to the National Science Foundation, US Ignite, researchers at the University of Southern California, gigabit connectivity, and high-resolution microscopy.
Marine biologist Professor Dave Caron has just started teaching a class at USC with remote students at STEM School Chattanooga.
STEM students in Chattanooga, home to the country's first community-wide gigabit network, are experiencing biology and STEM like never before.
So what's exciting is that we've taken a digital cinema camera that would normally be used for making Hollywood movies and combined it with this microscope and put it under remote control so you students in Chattanooga can actually move the image.
It makes it look 3D by the different shades and different colors.
The interactive high-resolution microscopy system enables researchers at USC to place live biological specimens under a digital cinema microscope and capture ultra-high-resolution movies of the microorganisms while simultaneously transmitting live, high-definition images from the microscope system to students in the STEM class. Under the guidance of the USC biologists, STEM students can enhance their learning further by manipulating the microscope effectively at very low latency levels.
When our teacher first talked to us about it, she was like, you're going to be able to control the microscope. And we were just like, oh, okay, cool. We get here and it's all these fancy controls. So you've got the big screen, and we were just kind of in awe.
The project represents the first to integrate digital cinema, optical microscopy, aquatic microbiology, flat panel displays, and gigabit networks into an educational environment in a scalable fashion.
So this project really represents one of the first attempts at that.
I mean, we're in Chattanooga, Tennessee, and that microscope is in Los Angeles.
1,800 miles away.
1,800 miles away.
1,800 miles away. It was amazing to see kids that are harder to get engaged in science or think they're not good at science. They were engaged almost instantaneously when they saw these microorganisms on the screen.
Are there any questions? And we couldn't even function with words how to explain how cool this was.
I got to like play with microscopes and stuff, but they never really grabbed my attention, to be honest. Actually getting like to see specific things moving around, and then all you had to do was like ask, and he knew like exactly what it was. Like, I thought that was really cool.
The microscopes I've used before have an image like this big, so this is a drastic change.
You could actually see little organisms moving around.
A lot of 10th and 9th graders who would walk by and like scoot over and glance, be like, oh, what are they doing? I want to be able to do that. I hope we get to do that next year.
As an educational tool, this project gives students the opportunity to see, appreciate, and understand the complexity, beauty, and science of the micro world that surrounds us.
Having access to top research scientists and equipment that's only available at USC, these students are going to be able to do some groundbreaking research that hopefully is going to foster a love of science.
The impact on subjects like biology could be enormous, with thousands of additional high school students becoming inspired to choose the
Okay, well, that goes on for a little bit, but real-time communications, because the students are moving the microscope, panning back and forth, the slide, they're changing the focus up and down, and as they turn that knob, they're looking on the 4K screen, and when you start turning the knob, you want to see the focus changing on the 4K screen now. And you remember, it was 1,800 miles away. In order to make this work, we worked together with Internet 2 to go and form a separate piece of their network on AL2S, Advanced Layer 2 Services, and plugged in that directly, the AL2S, from a Genie rack in Chattanooga to the Genie rack at USC, using the Genie network, which uses this Advanced Layer 2 Services across the country, to form a low enough latency path that we could get this to work. So very real-time communications that required a lot of network tuning in addition to the low latency on both sides to be able to make that actually function well. On the right, you can see an instructor who is being inserted in 3D live into a virtual reality. And this is for teaching high school students. These are both high school student projects for educating high school students. But on the right, he is showing how things work in a solar energy plant. And let me just play a little bit about that. But remember, the interesting thing here is the real-time communications needed to put a real live instructor in real time into a virtual reality for the student. The instructor in the particular video you're going to see is actually about 1,000 miles away.
I'm Christoph Borst. I'm an associate professor of computer science from the University of Louisiana at Lafayette. This is Sam Econ. He's one of the research assistants on the project. We're using virtual reality for education about alternative energy resources. So we're trying to teach high school students about the concepts of energy production, specifically a solar array. The virtual model allows students to take virtual field trips of the facility. These are students who may not be able to visit the real facility due to geographic constraints or scheduling constraints. We have delivered this to 3 high schools in Lafayette, and now using the high-speed network, we could invite schools from other cities to join in.
What's interesting to me about this application is definitely the streaming of the teacher to any place remotely. The ability to have someone there, but not really there to guide you, and to someone that actually knows about the things that you're looking at.
The network aspect of our project is that a real expert from the Energy Center can join the student and give the instruction and assess the student's understanding.
We're using Oculus Rift DK2, a Razer Hydra Connect on the other side back in Lafayette. and a very powerful graphics card to drive everything. Right now, I'm in place of a student, and the people in front of me are the experts for the facility. Right now, they will be describing what I'm looking at and telling me facts about the Energy Center and the benefits of us being here remotely.
Through US Ignite, we have access to the high-speed network that enables us to do this, for example, between Lafayette and Austin, like we're doing here today.
So again, that network between Lafayette and Austin was done over Internet 2, AL2S. Again, special arrangements. We got one of the engineers for Internet 2 to actually bring a branch of Internet 2 into the exhibit hall in Austin and have the other end connected at the University of Louisiana, Lafayette. Again, off a Genie rack on the Genie network to get that kind of low latency to happen. So let's talk a little bit about public safety. On the top left is a project that uses a drone flying one circle around an accident to be able to go and produce the entire accident report with all the distances. Right now, they often go out with measuring tapes to go and measure the length of the skid, length of that, length of the other thing. That can be greatly reduced with this drone. This, on the bottom left, is the Louisiana Business Emergency Operations Center. In Louisiana, the Emergency Operations Center gets additional information that's given to them by a business network and is filtered through this Business Emergency Operations Center. And businesses also get information back about whether they need to close, if they have needs in the emergency sector for certain goods, which the businesses can provide. Just a synergistic opportunity to go look at both of those. On the left, on the right here, your right, now my right as I turn around, is part of North Carolina. That storm surge is being predicted in real time based on the current winds being reported. Real time is very important if you're dealing with a hurricane, such as the one that just hit. This is a simulation from an earlier one. I don't have yet a video from that. I'd like to show you, however, a video of looking through the pavement. So in the top center there, you can see the pipe. It's going through a wall there that's going and holding that pipe in place. And you can see some of the branches in green up there going in and out. And imagine you're the public works supervisor where you put on the headset like a Microsoft HoloLens. You're still seeing the outside, but in 3D, your visual depth is telling you you actually have X-ray vision. Let's go look at that.
I'm Driver Houston from the University of Vermont. I'm a professor of engineering.
I'm Dali Wu from the University of Tennessee at Chattanooga, assistant professor in computer science.
My name is Hugh Liang, faculty in the Computer Science Department, University of Tennessee at Chattanooga.
We're applying smart cities technologies to the problems that come with underground infrastructure, looking to map and assess the conditions. What are issues with underground infrastructure? Well, it's the lifeblood of all modern cities. So you have water, electricity, gas, steam.
For example, we have applications augmented reality or virtual reality based mapping of underground infrastructures. So those applications, it requires high-speed networking and also high-performance computing.
Well, at the moment we have 3 communities involved: Burlington, Vermont, Winooski, Vermont, and Chattanooga, Tennessee.
We prefer to use high-speed networking as computing technologies to transmit the information about underground utilities to workers, managers, and city planners.
That's the ground-penetrating radar equipment,
we want to transmit real-time information to people on site.
There's lots of really cool technology, but also folded into that is the ability to make a big difference for these cities, make their situations much better.
And then the real-time communications part is streaming the portion of the public works database that they've created with this underground penetrating radar to the HoloLens based on where the HoloLens is looking. So as I look to the right, to the left, I may need different parts of the map to be able to come into the display. And it has to be done very quickly, because if you don't do it within 5 or 10 milliseconds, people will begin to feel seasick in those virtual reality displays. So streaming virtual reality, certainly one of those applications. So looks like, what do I have next? I think I wanted to talk a little bit about, so what's different about these apps? Why does real-time communications happen? What are the categories of these apps? And here's the way I see it. The people who use real-time communications are using it for one of these reasons. And this is after looking at a few dozen applications that use real-time communications. The first is there's probably some kind of collaboration. Maybe it's people working together. I have an abiding faith that if we can get rid of a lot of the latency in video conferencing, if we can give up on MCUs, if we can go directly between cameras and other ends over low latency networks, that video conferencing will double in volume, will be much more effective, will be much more educationally effective, and we'll use it a lot more. So I really believe that real-time communications and video conferencing, we keep detuning for the internet we have instead of upgrading the video conferencing for the network of the future. So the network of the future, I think we're going to see increasingly gigabit, less congestion, the ability to prioritize. Now that we've done away with network neutrality, we're allowed to prioritize, right? I'm trying to look for an upside here. Give me an upside on getting rid of network neutrality. So maybe the upside of getting rid of network neutrality is that we can go and give these applications some kind of a priority. People go and look at this and they say, but the video, I mean, you don't need that much for video. I can watch Netflix, and the video rate that I need is only like 3 megabits per second. That's true once you go and compress the video. I used to run National Lambda Rail. I was CEO of National Lambda Rail. One of the big things we ran on the 8 terabit per second network was uncompressed movies being sent to supercomputer centers where they would use 2 weeks of supercomputer time to get compressed to commercial release quality. They would go over it that many times, forwards, backwards, motion vectors, submotion vectors to go and produce the, where will we put keyframes, where will we put other frames to go and really get this bit rate down. If you don't have 2 weeks to go and move your 4K data, for example, on the microscope, you know what the data rate is feeding that 4K screen? It's just a bit over 2 gigabits per second. That's what it took to produce a rotifer that you can see with its cilia moving for the kids, because we did not have time to compress it. Compression is great if you've got time, if you're not interactive. But if you're doing real-time communications, real-time video, and being interactive about it, that requires a lot more bandwidth at the moment, unless any of you can come up with an instantaneous compression algorithm, which no one has done yet and may be impossible by the laws of mathematics. We will see. But those are the kinds of things we need to think about on real time. So that's collaboration. It could be person to person. You could be manipulating a common model. Can you imagine somebody who's doing some engineering work and they need a industrial engineer for how does this look? They need a safety engineer for is this going to be safe? They may need a structural engineer. Will it hold together and be durable? How do you get those engineers and other people, a marketing person, does it look good, into the same room looking at the same thing, modifying it, making changes, and doing things like that. So I think that that kind of collaboration is going to call for more real-time communication. My second big category is projecting some kind of a resource from one place to another. You could be projecting the intelligence to a gigabot. You could be projecting the microscope into the classroom. You could be projecting the underground data structure into the supervisor's headset. There's all kinds of projection of things that mean that you need real-time communications, because the thing being projected to can move or say, I want to look to the left or the right or up or down. And all of that means that you have to be able to complete that loop and in very low latency bring it back so the person thinks it's running. And the goal here is simultaneous with reality. How can we make it seem like it's part of reality? Why does digital have to be slower than reality? The instructor into the virtual reality. Okay, cyber-physical systems. These are classical. These are studied. These are systems that live partly in the digital world, partly in what we're today calling the real world. I think in the future, we may call this combined world the real world. I think certainly my grandkids will. But at the moment, I'm going to go and say there is a distinction between the digital world and the physical world. And the cyber-physical systems work in those areas, like the brain stimulation tuning, the microscope controls, and there's a whole bunch of building control systems, indoor location systems, all of which need this kind of cyber-physical system, close the loop, get people to move in the right direction, do the right things. So these are the kinds of applications that I think do that. I'd like to talk a little bit about how long they take. So those of you who are scientists and engineers will recognize the log scale of time running from left to right. And I want to work from the right. I want to work from the macro here, from the 10-second on down. So there's a set of applications that run and respond in these kinds of time frames. If you actually go and time a loading of a web page from your bank, from Amazon, you're going to find out that it's probably over a second. Average load time is 1, 2, 3 seconds if you actually go and measure it. Sometimes you can get some responses that are faster than that. If you're running Gmail and you notice that when you hit on inbox, it shows up instantly, that's because it's pre-cached in your browser, and it can go and pull that up. But if there's anything new, getting it over the web is kind of in the 1 second range. Buffered movies is great. You know, once we go and we get the movie coming to you and we get several seconds of it buffered, then, you know, that works fine. A few seconds of buffering, no one is complaining about these days. Skype is kind of a little bit less than that. But I think I can group all the ones here to the right-hand side as traditional cloud-compatible applications. You can do these with traditional remote clouds. You may have to go and tweak the protocols a little bit, which would they do in Skype. The 3D rehabilitation is right there on the line. I think the next challenge is how do we move this box to the left? How do we get this next bunch of applications? Anyone here a serious gamer? Anyone using Twitch? I mean, the people who are serious gamers want to trash talk to each other in real time. They want real-time communications faster than today's internet. And they're putting up their own local internets to go and do this because they can't get it out of today's traditional internet. And they may not have the pull with Internet 2 to get their own private network cross-country to be able to make that work. So how do we get human robotic control, haptic telesurgery? Right now, if you get robotic surgery, the surgeon is actually in the next room. We don't do that at a distance yet. But how do we get the best surgeon when you need it, even if that best surgeon is 1,000 miles away? In order to come down into this next thing, I think we're going to need to look at edge clouds. Because we're working against just the speed of light, right? The Einstein speed of light, that's the one constant in the universe. And we can't go too far away and get that. So instead of being able to go and get Internet 2 to go and put up a connection to the microscope at USC, guess what? Chattanooga is buying a new microscope they're putting in Chattanooga. And now they'll be able to use their local access network. We won't have to tune up something that goes cross-country for those students to be able to do that kind of science. So edge clouds, I think, are going to be able to do this. If you go at shorter time frames than this, you need more real-timeness than sort of human interaction or on the edge of human interaction. Then we are already using dedicated hardware. That's what we do. We go and we put dedicated hardware and satellites and things, for example, if we're doing something that is robotic and it needs to go and adjust itself right away, there's a dedicated computer sitting right there. And in fact, anyone seen the Magic Leap that just came out less than a year ago? I haven't either, but apparently that comes with a 12-pound computer that they put on your back so that you can go and have that, because we're unable to do the real-time communications well enough to separate us from that 12-pound pack. So I think this area to the left is kind of the unexplored frontier. And what we'll do over time is kind of take this and drag it to the left. And as we drag it to the left, there's more applications. The applications that I can think of are kind of there and kind of go down to about a half a millisecond, which very conveniently is the 5G standard for what their latency should be. So there is some congruence there. But I'm guessing there are a bunch of applications off to the left here that we just are not good enough to think about yet. We haven't figured out what those are. So I thought that I would talk for just a second on this merger of the digital reality and physical realities. So the biggest mass version here was Pokemon Go. Remember these little creatures that would appear on your screen and that would appear to be there even though they weren't there? But as far as you were concerned, they were there, and you could go capture them, and you could have them fight each other or something or another. I'm not sure exactly what all. But that kind of really popularized the merger of these realities. On this side is from one of the movies where futuristically they can go into the smart city and they can go and understand what's going on in the smart city, and just by touching a digital version make things happen in that city, real-time communications, right? So one of the people I think who's done the best at merging virtual reality and physical reality is a company called The Void. And I'd like to go and play just a video here. Notice how the virtual and the physical realities are being merged. That's the key thing. That's physical, but this is what she sees. Here's the physical. That's what is actually happening, but this is what he sees. Here's what is physical. This is what he sees. Physical. They're putting the virtual on top of it. You can touch, you can feel that because it's actually physically there. That's what's happening in real life. And this is what's going on in the world that they see and can touch and can feel. Okay, look like fun? So this is done out of a company out of Linden, Utah. And the whole idea is not only should you be able to see and hear virtual reality, you should be able to touch and feel it. So they use the motion simulators, and they use, in the case of pressing the buttons, it's just a piece of metal right there in front of you, and as your finger touches it, you feel that the metal is there, like you're touching buttons. And then, of course, what you see is that you are touching buttons and that things are happening. So I think that's really very interesting for that kind of a merger. Okay, so some supporting technologies. Let me see how much time I've got here. Okay, just not too much, but I'll go through this kind of quickly. We have examples from existing cyber-physical systems. We've learned a lot about autonomous vehicles. This is an F-5, the first fly-by-wire airplane. A lot that we know about from smart buildings. That's now quite standard. Real-time systems. I think at a real-time communications conference, I needn't talk about real-time systems. You all understand these things. And how, for example, a Segway balances. So we can learn from that. Local and edge clouds, because we need to have the communications happen more at the edge. Communications that happens at the edge means that it can be faster, travels shorter distances, doesn't go as far, doesn't go to some distant peering point, can happen right away, and we can get much lower latency. And Glenn believes, that's me, I believe that in the future we'll think less about what the bandwidth is and more about what the latency is. Because for every application I've shown you today, the latency counts just as much or more than the bandwidth, the application latency. And so we're going to think about that latency as being the key measure or metric of what we want to have by use going forward. So there's a lot of things going on. Just a little bit later this month, the third ACM IEEE Symposium on Edge Computing. It's going to happen in Bellevue, Washington. They were nice enough to let me keynote their first version, their first edition. Amazon Web Services has Greengrass, which is their edge computing. They realize that not everything can happen in Amazon Amazon data centers. So some of this is going to happen out further. Paradrop comes out of the University of Wisconsin. OpenFog is a consortium where the fog is kind of the cloud that's much more local to you. You're in the fog. US Ignite is working with the National Science Foundation on something called EdgeNet. That's edge-net.org. Go look into edge-net.org. It's an alpha right now. And these are attempts to go and make the local communications work as effectively as possible with an eye toward latency as being the main requirement. Sometimes bandwidth counts also, but latency is the key issue in all of these systems. Advanced cyber infrastructure. I think we've talked about the fact that we need some of this occurring on the edge as well. We know a lot about it from supercomputing centers. Tokyo has the AI bridging cloud, which I think is really very interesting. There's some big data things going on here, connected vehicles, real-time image analysis, information fusion that I think we can use. And the other thing that I see especially valuable at the edge is biomimicry, the ability to go and do neuromorphic computing, to do computing like the brain does it, to think in that way. And through chips like this, we can reduce the latency of serial computation, of giving a computer this list of instructions to execute, and instead do many things in parallel in a natural way. I think that's going to be very important going forward if I'm going to reduce the latency and the response time of these applications to make them sort of synchronous with the real world. We have, as people, 3 different nervous systems, but let me just talk about 2 of them here. The somatic nervous system and the autonomic nervous system. The autonomic nervous system causes you to breathe, even when you're not thinking about it. It causes you to go and pull away from something hot instinctively. And then there's things you think about. I think I'm going to go and hit this tennis racket over here. To have this kind of 2-level thinking, one part that goes on automatically, another part that goes on when you think about it, would seem to be part of what we need to have a very realistic real-time communications, things that happen automatically and then things we individually think about. I think I'm going to skip this Nobel Prize in Chemistry video because of time, but if anyone wants to stay later, it's really kind of interesting in that it shows how the chemistry in your body operates in real time. In fact, at 1,000th of a second. And you don't think of chemical reactions happening at 1,000th of a second, but we know from studying the brain and from things going on in the body that things are happening on that kind of real-time time scale. And so that's important. Let me finish by saying synchrony with the real world implies responsiveness, implies feasible locations, which means the edge, thanks to the speed of light. There's going to be multi-tier, multi-edge applications. You've seen some of them today. And that means we're going to need within-app networking, which means distributed systems are very important in terms of going ahead. And distributed systems with locality mean we need more local-only network traffic, more east-west network traffic, as opposed to the north-south traffic that we see for distant data centers. And that's going to cause a change in how we think about networking. And that local-only traffic then means that city-scale data center-like network of architectures, I believe, is going to be the next edition of the internet. Make sense, Ken? Okay. So we do have a US Ignite testbed that you can go and try out these things on, and I encourage you to do it. So we're implementing this local testbed, I call it a digital town square in all of these cities. The digital town squares for local exchange of local traffic. We're using EdgeNet, the Genie network, and AWS and anything else. I'm going to skip that slide, skip this slide, because I want to get on to, I think, yeah, I'll just stop right there. So do I have any questions? Thank you very much. I think I've got like 3 or 4 minutes for questions. Yes? You had a question? No? Yes?
So just you mentioned yourself that the human body's responsive and ability to transmit electrical stimuli is relatively slow, like 100 miles an hour, that type of thing. So you're actually talking about real-time communications well beyond what the human body can achieve, yet we see real-time at a fairly slow rate. So, are you exceeding what the human body actually wants to achieve in terms of what is real time?
Well, that was kind of the point of my orange oval diagram moving to the left. I think that we're currently in the stage where we are attempting to get as fast as humans, which will cause us to be able to fuse digital reality with physical reality. And I think that is going to be a big mark in what happens in the world of digital technology. Once we can get digital technology that's as fast as we are, I think that's a big milestone. People are not microseconds, but I think that there is another world, as I said, that will go even further, because mechanical and electrical systems do operate on either time or time scales. So if you're managing an electrical grid and you have a synchrophaser, that synchrophaser is looking at microsecond-like things. And we probably want to synchronize that. We do synchronize that throughout the electric power grid. So if that's going to be part of our reality as well, then we have to do things which are faster than we are. Our devices, IoT devices are faster than we are. So I think there's a big kind of, when the first human can be beaten in chess or in Go, we're reaching certain human-like stages, but we will go beyond that. Yes?
Already run faster than human time.
That's true.
Program trading, flash trading.
Right. Do you know why a lot of financial networks do not use fiber? Because of speed of light. What's the speed of light in fiber?
Slower than in air.
Yeah, about 0.6 C, whereas they use microwave, which is about 0.95 C.
Chicago to New York.
Right, so we're seeing a renaissance in microwave communications because it's faster than fiber. And by the way, it's also more direct, right? The fiber is going hither, thither, and on up the street, over there, down, left, right, back, whereas the microwave can just go point to point. So I agree with that completely. 2 more questions.
You've given us an inspiring overview of what might happen for the future, including things like public infrastructure and public safety. So I'd like to ask a depressingly practical question.
Shoot.
Which is, obviously, everything you're describing requires a lot of scientific ability, a lot of technology. How do we bring that into the government space?
Well, as I said, US Ignite works at the intersection of industry, government, and academia. And so we're trying our best to educate what's going on. We try to involve politicians in each of our cities to give resources and cover and support for these activities, because otherwise they just get eaten up. Some of these things are new ideas, and they just run up against, well, this is how we've always done it. And the best thing we know to overcome that is political leadership. So, for example, in one of our Smart Gigabit communities, Moreau Weinberger is the mayor. His main re-election campaign, now this is in Burlington, Vermont, was US Ignite in our city, was the main promise. And he got re-elected with 65% of the vote. So once you have leadership like that, and then he promoted his chief of police to be the chief innovation officer in Burlington, Michael Sherling. So when you do those kinds of things, then you can affect the city. But it's one of the reasons that you did not see New York City up there. They were just too big. We talked to them, but there were too many various silos already there that were going to be difficult to get across. So a lot of the cities are smaller cities because they can be more nimble. It's an advantage for smaller cities. You can get there more quickly than can the largest cities. Last question. All right. Well, thank you very, very much.